Hi, everyone. Thank you so much to organizers for putting together this wonderful conference. I'm going to be talking today about a archival search through TESS data with the intent to search for free-floating planets, a surprising signal we found, and what that implies in terms of challenges for future space-based microlensing missions, notably Roman and Earth 2.0. So I don't have to convince you that this is a very exciting time to be in microlensing. Roman's going to detect hundreds, if not thousands, of FFPs in the next decade. But along with that, there are emerging classes of false positives that are going to present a significant challenge for future analysis. So at this point, we need robust automated pipelines to deal with the massive amounts of data that we're going to be receiving. And so that provides the motivation for this search to repurpose existing archives of high-cadence space-based observations to prepare for Roman and Earth 2.0. So let me introduce TESS to you if you're not familiar. TESS stands for the Transiting Exoplanet Survey Satellite. And to meet its mission requirements, it was designed with a high cadence, a wide field of view, and high photometric precision, making it well suited for detecting short duration dimming due to the transient method. But as you'll notice, this makes it in principle sensitive to other short duration transients, notably potentially microlensing on short duration scales. So to explore this idea in a little bit more detail, we conducted an initial search of sectors 61 through 65 in TESS, which currently has a little over 70 sectors of data. And I'll walk you through a little bit of what that pipeline looked like. So I can go into details about every single step in this short talk, but I'll just highlight a couple of key characteristics. One of the first steps is a BLS or box least squares search. And the point of this step is to simply identify as many brightening events in the data set as possible. We're working with millions of light curves from individual stars. And so to pare that down into a more manageable amount, this is a nice first step. So what we do is search for isolated, non-repeating, short-duration brightening events, keep those with a signal-to-noise ratio that is sufficiently high when comparing the event, the height of the event to the red and white noise outside of the period of the event. And this is nice because it's GPU optimized. You can do this in parallel and pare down your initial catalog. The other feature of the pipeline that I want to mention that happens at the flux level is an asymmetry cut. And this is to rule out anything that's not symmetric because we expect most of these short duration events to be symmetric. In the back of our heads, we're imagining that this will kill off the majority of flare type events. So this is just done in practice by fitting a speed normal distribution and removing anything that doesn't have sufficient symmetricity. Okay, so starting from 7.5 million light curves, after going through this, and as well as some pixel level vetting that I can't really get into, and lastly, manual vetting of a couple hundred signals, we end up with one remaining candidate, which is quite intriguing because it exhibits a light curve that is very consistent with that of microlensing. And this is confirmed across independent light curve extraction methods and is not identifiable as repeating in other test sectors for which this source appears, of which there are two others. So at the very least, this model merits some detailed modeling, consistency checks, and comparison with known and unknown false positives. So at this point, I'm going to branch into two parallel sections of the talk. In the first, I'm going to work under the working assumption that this is a microlensing event in order to do some sanity checks. And so I just want to make it very clear, this is just working assumptions so that we can model it and treat it appropriately. So a remaining candidate has a light curve morphology that is consistent with microlensing. In particular, it is better described a finite source point lens model. From difference imaging, we know that it is an isolated source. There's no blending. We do fit for blending. It's consistent with 0. So it's a relatively clean signal. And luckily, because it's a nearby source, we have information from Gaia about it. So we know its size, we know its distance. So this is a sort of a rare case compared to what you're probably used to. And so we have additional information about the angular size of the lens. Again, under the working assumption that this is a bona fide event. So as a simple sanity check, you might want to check whether the physical characteristics implied by this are consistent with a low mass free floating planet. And indeed, with very large error bars, even in the worst case scenarios, the model is well represented by a sub or slightly super terrestrial mass lens, about half a kiloparsec away. For reference, the source is about 3 kiloparsecs, moving at typical galactic local velocities. So, this is not meant to be comprehensive, but as a sanity check, certainly the physical parameters of the fit are consistent with a planetary mass lens moving at a reasonable velocity. So what's the catch here? Why am I being so hesitant to take a stance on this so far? Well, one reason is that the detection probability over the entire TESS catalog is quite low. As I mentioned, it is a transit survey, so it's not optimized for microlensing. And from its detection efficiency based on its cadence, the relatively short window at which it observes each TESS sector, and the relatively shallow field of view that TESS has, limiting its optical depth, we find that with the best fit, assuming et al. 2023 power law, we would only expect one event over the entire TESS catalog, and we only search through 5 sectors. So, assuming these follow the Thomsonian processes, that's ballpark 5 to 7% chance that we saw this. So, did we just get extremely lucky? No, we should be, very cautious moving forward. These events are certainly quite rare. Therefore, we need to consider other possibilities that might be more likely. And that's where I will branch into the most likely false positive interpretation that we considered, which is that of a flare. And I'll work under this assumption and then again see what that implies. So the first real damning evidence against the microlensing interpretation is that we know our star is flaring. There is a small feature in the TESS light curve detected 2 weeks prior to the primary event. And for this, flare models are overwhelmingly preferred to the finite source point lens and also a point source lensing model. So this indicates our star is magnetically active, it's known to flare. And so you might just want to exclude this from any sort of general FFP search if you want to be very conservative. But because the primary event, which is what is picked up by our BLS search, is much larger than this, that was what we performed all the cuts on. And we can't put the genie back in the bottle. We've already seen this event. It's still unique. And at the very least, it's a rare astrophysical phenomenon that has not been explored in the literature. What do I mean by that? Flares have been studied. Why is this one not thoroughly explored? And you'll recall earlier, I said that we did a cut on asymmetry. Shouldn't remove the majority of flares. And you're right, this does remove the majority of flares. However, it was pointed out by Rouge in response to our paper that Algol has observed some flares that appear by eye to be very symmetric. So I can't tell personally looking at this. I can't distinguish this from my cleansing. I can't distinguish this. Certainly it doesn't look like a characteristic sharp rise and exponential decay of a flare. So in light of this, we want to go back and check if our event, our primary event, could be an example of symmetric flares. So we can calculate what roughly the energy released by such a flare would be by fitting a flare model to it and integrating over the time of the event. And what we find is that the total energy released would be over 2 orders of magnitude larger than all 9,000 flares that were observed in the first 2 TESS sectors. So if indeed this is a flare, it is a highly unusual, super energetic flare that is certainly unique in the TESS dataset and unique as far as I know in general. So already this is a little bit problematic. But to do our due diligence, we also conducted a retroactive search for other signals in a flare catalog that appear by eye to be symmetric. Notably, all of these would have been eliminated by our automated pipeline, but even if it made it past that and was at the point where we're doing detailed modeling, these are all better fit by flare models, Pitkin and Davenport specifically, than microlensing events. So even at the level of data, these do not hold up. So this is all to say that our primary event is still unique in that it is not distinguishable from microlensing at the level of simply the data of the light curve. And I should also say, there is no current model, there's no data-driven model for symmetric flares, so there's no likelihood we can evaluate to compare a symmetric flare with microlensing, which is a huge gap in our knowledge currently. So where does this leave us? So in retrospect, TESS's 27-day per sector observation window really limits our ability to characterize source stars. That means it's difficult to rule out false positives. You're only observing for a short time. And additionally, there is longer baseline data available on the source that suggests it does have a low amplitude variability with a period longer than the TESS window, indicating that we would not be able to tell if the star is variable with a duration longer than roughly a month. With that said, we did look into other sectors in which the source is observed by TESS, and there were no repeating events. There was nothing remotely similar to this odd blip in sector 61. So the best we can say is that neither explanation, and we couldn't come up with any explanation more likely than these, but neither explanation is likely at the level of data, at least not quantifiably. And so on the flare side, we don't have a likelihood we can evaluate. And at the very least, these events are incredibly rare because they are not well cataloged, at least ones that are consistent with the morphology of microlensing. And on the microlensing side, the morphology is good, but it is definitely in tension with the expected rate of events. And the source is known to exhibit variability, meaning we should be extremely cautious. So that is all to say that the event is interesting and merits consideration, and it might belong to a new class of pernicious false positives that future space-based microlensing efforts will have to deal with one way or the other. So with that, I'd like to thank you for your attention and also thank my collaborators, Michelle, Will, and Steve, as well as conversations with a number of you in this room today. And additionally, our anonymous reviewer who provided really critical insight to our paper that significantly improved the manuscript, the final version of which has all these updates in it, should be coming very soon, but you can check out an older version of our paper here if you'd like. And with that, I'd like to take any questions.
Just looking at probability, it looked like a sort of frequentist type probability. So a sort of Bayesian probability. I just wonder what probability, if you accept the event, probabilistically is it in tension with models that are hinted at by other microlensing surveys for the free floating planet? So looking from a sort of Bayesian perspective.
Sure, good question. So I think in the sense that the mass function that we're fitting to, assuming a mass function for the power law, is data-driven, it's hierarchical from a population model. That is what is informing this predicted event rate. So the combination of that population model for the free floating planets and TESS's particular cadence, observation duration, and where the sources are located, the optical depth, et cetera, that can all now sort of be directly calculated. So there's this 5% number does not come. And you need more in depth than that. Simply, if we take the average number of events over the entire catalog, what does that imply for looking at 5%?
Still not clear that's the same as what I'm asking, which is if you accept the event is true, what is the exclusion confidence of the inputs that you've put in to get that number?
I don't think I've done the calculation I'm talking about. If we take it as true, yeah, the most I can say is the only claim that I was trying to make was about the probability of seeing at least one event, which is unlikely if we. But again, if you're raising a very good point. So again, I did say I was considering the central power law, but as we talked about in depth today, there's a lot of uncertainty on that end. So this number could be quite a bit lower, quite a bit higher. But at the very least, we're looking at a mass range that is not, there's no direct observations in the terrestrial masses. And the only thing we can say is that it's certainly rare, but very difficult to quantify.
So I actually got a question. For the first semi-all search for for planets in 2011, I also did a paper on some like short binary events in that sample. And one of them looked like it was a pretty low mass planet where there's a signal from a planet at constant, but no significant signal from the host. But you'd also be pointed out that it's a location of an M4 star. And so that looked like there was a star at the location of the event. It was M star, and M stars tend to have larger amplitude fill errors. So we checked with some M star flare experts and asked what the probability of like a 1 magnitude flare on M4 for quiescent one, and they said, oh, it's very rare, maybe once every 400 years, and so that may be rare for flares, but it's pretty common. I mean, it's way more common. So have you, in your sample, what fraction of the stars that maybe could detect a signal like this on were M stars?
Well, that's a good question. I don't know about our source population, what the characteristics of the stars are on average. But regarding the relative probability of these, we're estimating from a catalog of 300 such events such as these that are reasonably large signal to noise. We estimated an occurrence rate of about 1% because we're narrowing down 3 from a population of about 300 we considered. So that's not saying anything about the source itself, but symmetric appearing flares are certainly quite rare.
Is it the source a K giant?
Good question. It's I can tell you a little bit about it. It's got a radius of about 13 solar radii. I'm not sure what class that represents. I don't remember the picture off the top of my head.
Small comments about flares, so they can do frequency events or models. And maybe we made it last year, 2 of the frequency events for errors, 3 were actually turned out to be flare events. And then actually we have the other discussions about this and the stars. Here for all one, mathematics is very important that we have prediction of low mass stars as a source of prediction. So it means the statistics of this actually of the star mass that we're known to start trade more slightly brighter with the current frequency survey. So that's my point. That probably would have maybe a higher background of flaring stars where we are studying the format, especially when we're looking for problem.
Yeah, so in Opal we looked at the flaring stars. So we have a couple of spotted stars that show some very individual star spots, and they also exhibit flares. So when you extrapolate from that, so we saw a couple of such symmetric flares. And if you extrapolate that back to the TESS sector, you observe still the probability that even is because the flare is much higher than the probability of finding very mass planets somewhere in the galactic plane, very far away from the galactic center. I have a question about future TESS observations. I know that this source is supposed to be observed in TESS sectors 87, 98. Do you have any data from that?
Good question. So 2 days ago, I checked on MAST, and there's not any additional sectors since this work was put out for this particular source, but we're certainly looking forward to it being observed again in a future. For people. Sure. Sorry for people on Zoom. I did check this a couple days ago, and there's not currently any additional sectors other than what I showed in this work that have been observed. So I believe in the coming months we will hit. So sometime this year, I believe we're hitting the source again. So I'll be very curious to see if there's any other sort of unique features particular to this source. And just a plug for what I hope to do in the future with Michelle and Will, Steve. I think at the very least, this motivates looking through the rest of the TESS sectors to try to catalog false positives as well as possible and see if we can find anything like this or something similar.
Okay, I just had a comment related to JP's point. Basically, for Roman, the source stars for free floating planet events are going to typically be brighter than the source stars for bound planets, just because you need a higher signal to noise to rule out false positives, and with a brighter star, that's it. Yeah. But also, we should look carefully at the colors of the stars to see, and maybe exclude some of the samples based on that.